Okay, we're going to continue our discussion of alkanes, and I think the last thing that we had done was look at the preparations of alkanes, and we had gone through the heterogeneous hydrogenation of alkanes using supported palladium or platinum, supported in either charcoal or asbestos. We looked at the fact that those hydrogenations, particularly of alkenes, were syn hydrogenations. They were occurring on a catalyst surface, and so they were coming on from the same side of the molecule. And that we would do hydrogenations of alkynes, and they would go all the way into alkanes. I did mention that there are techniques which you would meet in second organic, where you could go from the alkyne to the alkene, and then you could do so with specific geometry, but that's a bit beyond our course for now. We also said you could prepare alkanes from haloalkanes, and we identified zinc acid reduction. So, for example, I could start with, let's say I could start with this compound, and I could convert it with zinc and H3O plus into the corresponding alkane. I also mentioned that you could change H3O plus into D3O plus or T3O plus and introduce a label at that position. We could also get here by first converting the haloalkane with a metal, and it's typically lithium or sodium or magnesium. And you could make the organometallic, which for now I'm just going to write as Rm. And then you can treat the organometallic with H2O and do an acid-base reaction and end up with your alkane. So there are a couple of ways in which we could convert the haloalkane into the alkane. But where we ended last day is saying, well, these two methods, either the direct reduction or the zinc acid reduction, or the process via the organometallic, followed by H2O, D2O, T2O. Those don't change the number of carbons. But there is a technique in which we can take a haloalkane and convert it into an alkane with a larger number of carbons. And that method is one of the more important ones, and that's called the Corey-Posner Whiteside's house reaction. And that reaction occurs in a sequence that we're going to try to describe now. So essentially what this reaction does is it takes Rx, and again X is a halogen, and reacts it with an R prime X, and there's a series of reactions to generate R prime. Okay? So I'm going to have an Rx, methyl ethyl propyl butyl, to react with another R prime X, and that could be this R prime and the R could be the same group or not. And through a series of reactions, we generate R prime. So we're taking what you might call lower haloalkanes with fewer numbers of carbons in them, and we're going to build them into a higher alkane. Okay. So how do we do that? Well, it occurs in a series of steps where we take Rx, and we're first going to convert it into the alkyl lithium RLi, and that's done again in dry ether. So we convert the haloalkane into the organometallic, the alkyl lithium specifically, and that gives rise to, again, that's our umpolon, We're going from R delta plus to R delta minus. What's interesting is, and this is where this is the brilliance of the Corey-Posner-Whitehead-House method, we're going to treat this species with cuprous iodine. Now, this is cuprous iodine, right? This is cuprous iodide, meaning it is copper 1 iodide. And what you end up getting is R2CuLi. This is called a lithium dialkyl cuprate. It's called a lithium dialkyl cuprate. Now, the balance equation, and again, none of these equations are balanced. We've seen this one before. This would be Rx plus 2Li gives rise to RLi plus LIX. That's the balance equation for this one. For this one, it will be 2RLi plus CuI gives rise to R2CuLi plus LiI. So 2 alkyl lithiums plus 1 cuprous iodide gives rise to the lithium dialkyl cuprate. And you make lithium iodide as a product. Now, again, most organic chemists don't really care what the inorganic products are, but it's a good idea to have a sense of what the balance equation looks like. Now, so I've taken R delta plus, and I've converted it first into R delta, I'm going to write this as delta minus minus minus. And then when I treat this with the cuprate, with the cuprous iodide, I make R delta minus. Let's talk about that for a second. In the same way that if I have, for example, R attached to fluorine, fluorine is more electronegative than chlorine, more electronegative than bromine, and so on. So if I would attach R, some alkyl group, to fluorine, the fluorine being very electronegative sucks away a massive amount of electron density from the R. And that creates a very negative dipole on the fluorine and a very positive dipole on the R. Chlorine is less electronegative and so pulls less, and so I get a smaller negative dipole on the chlorine and a smaller positive dipole on the R. And then as you might expect, bromine is even less electronegative, there's a delta minus and a delta plus. So often what organic chemists do to illustrate qualitatively that one site is more electrophilic, or delta positive than another, is you might write delta plus plus plus. That in no way suggests that this is 3 times that value. It just means there's a larger electron deficiency at that site, greater electron density at this site, with the delta minus minus minus. So and that's what I'm trying to capture here. That the R in the alkyl lithium has a much larger negative dipole than the R in the cuprate. And why is that? And it's really for much the same reason as the positive dipole changes. It depends on the atom to whom you're attached. In the alkyl lithium, the R group is attached to lithium, which is an exceedingly electropositive metal. So the lithium dumps a large amount of electron density onto the R, creating the delta minus minus minus, and if you will, delta plus plus plus. But in the other compound, the lithium dialkyl cuprate, what you actually have is the copper bound to the alkyl group. And copper is a much less electropositive metal. If you remember your Gen Chem, or if you may have done this in high school, copper is really low in the activity series. Lithium is pretty high up, and copper is pretty low. So copper really is not particularly electron releasing. And so you only end up with a slight negative dipole on that alkyl group. This is going to become of importance later on when we discuss why we converted a large negative dipole into a small negative dipole. And just to sort of say it, here the R is much more basic than here. So this R is more nucleophilic than that R. Okay, so what we did is, in converting the R delta minus 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 to R delta minus, we say we softened, right? We softened the electron-rich species. We made it more polarizable. We also, in making it softer, made it a stronger nucleophile and a weaker base. And that's going to become important in our discussion later on. Okay, so the bottom line then is we are going to do ompolon in step 1, do a charge inversion, and then we're going to soften the nucleophile from the strongly basic alkyl lithium into the strongly nucleophilic lithium dialkyl cuprate. Now that we are a soft nucleophile, we are able to carry out nucleophilic reactions much more easily. And so now I'm going to treat the lithium dialkyl cuprate with my R prime X. And so here, my nucleophile attacks my electrophile, and I end up with my R prime. So that's the sequence. I'm going to take my alkyl lithium, I'm going to take my haloalkane, convert it into the alkyl lithium in dry ether. I have to soften the nucleophile, so I'm going to go from the alkyl lithium using cuprous iodine into the lithium dialkyl cuprate. Now that I've got a soft nucleophile, which is, so this becomes a much more nucleophilic species, I'm going to have it attack my haloalkane, and that's going to give rise to my product. And this is interesting because when you look at how I've written this, clearly I can't have two electrophiles react with each other. This R is delta plus, that R is delta plus. Two delta pluses can't interact. So clearly what I need to do is to convert one of these into a nucleophile. I can't have two electrophiles reacting with each other. So what this set of arrows means is that it's a series of steps that we're going to undergo, which functionally will convert one of my RXs, this one or that one, into the nucleophile, and then have the nucleophile attack the electrophile, the other species, to give rise to the product. Okay, so let's put some faces on these, and then we're going to ask the question, does it matter whether I use Rx or R prime X? Right? What are the conditions under which one of the species is made into a nucleophile and the other is left as the electrophile? Does it matter? And if it does, why does it? So let's put some faces on these. And I'm going to assume that you'll rewind this as you see fit, so you can always go back to the scheme. I'm just going to assume it moving forward. So let's see some faces on these. I'm going to give you specific examples of reactions under the Corey-Posner-Whiteside-House reaction. So, for example, I could take, let's say I had 2-chloropropane, and I had cyclohexyl bromide, bromocyclohexane. I could carry out a series of reactions, Corey-Posner-Whiteside-House, and I could generate this compound. Right? Functionally, that's what I'm going to do, right? I'm going to marry the two alpha carbons. Right? I'm going to marry the two alpha carbons. So how does this happen? Well, I could take 2-chloropropane, treat it with lithium, dry ether, convert that into the alkyl lithium. I'm going to treat the alkyl lithium with cuprous iodide, and that generates the lithium dialkyl cuprate. Now, I want you to note how this is drawn. So it's clear in this case that the lithium is attached to carbon number 2. That's where the halogen was. And we're doing a metal halogen exchange. That's our ompolon, delta plus to delta minus. When I write the lithium dialkyl cuprate, I need to indicate to which carbon the copper is bound. And the way this is normally done is I will orient it so that I indicate by this line, by that bond, which carbon the copper is bound to, which carbon the copper is bound. So this clearly illustrates that the copper is attached to carbon 2. In other words, the nucleophilic site in the species is carbon number 2. Okay? So that's my lithium dialkyl cuprate. I'm going to treat it now with bromocyclohexane. And what will happen, as you might expect, is the species, right, if I were to draw the curved arrow mechanism for this, right, this is going to attack the CBr bond and generate, and lose bromide, and I'll generate my product, which is the substituted higher alkane. So that's going to give me my product. But it occurs to me, there's another way I can do this. I could have taken the bromocyclohexane and I could have treated it with lithium in dry ether, and that would have generated the cyclohexylithium. I could treat that with cuprous iodide, and that would generate the lithium dicyclohexyl cuprate, which I could now feed the chloropropane, the 2-chloropropane, to give rise to exactly the same product. So I could have made this product in one of two ways, and that's one of the beautiful things with a Corey-Poisson-Whitehouse reaction. You have flexibility in the path that you choose. So notice then that in the top version, I took the 2-chloropropane, and I chose to make that into the nucleophile, and fed it the electrophilic cyclohexane. In the bottom path, I took the electrophilic cyclohexane, and I made that into the nucleophile, and fed it the electrophilic 3-carbon species. And both of those pathways are perfectly reasonable. So the question then is, does it matter which I choose to make the nucleophile, which I choose to leave the electrophile? And the answer is that in the vast majority of cases, it doesn't really matter. But there are two cases where it does matter. So if in your choice of R and R prime, if your R is either a tertiary species, so if your Rx is either tertiary, or, so I'm going to put R here, or if it is such that it is adjacent to a quaternary site, so this site is tertiary, here the alpha carbon is adjacent to a quaternary site, right? This carbon has 1, 2, 3, 4 R groups on it. If your Rx falls into one of those two subclasses, you must make it the nucleophile, right? Then these must be converted to R2CuLi. If you left them as the electrophile, the reaction will not work. Or, worse yet, there will be a reaction that occurs that gives you the wrong product. Okay? So, under normal circumstances, it doesn't matter who you convert into the nucleophile and who you leave behind as the electrophile. The only times it makes a difference is when your substrate, your Rx, is either tertiary or the halogen is on the carbon adjacent to a quaternary site. When we get into the discussion of SN1 and SN2, particularly SN2, we'll explain in more detail why this is a problem. But for now, I will say that if you notice when we were drawing up the mechanism, we said that there had to be an attack by the R minus, if you will, on the positive carbon. Those attacks, for reasons we'll go into later on, have to occur from this side, from the back side. And when you have 3 R groups in that position, attack here is impossible, right? And so the reaction wouldn't work. And then similarly, in a case like this, the attack has to occur from the back side. And if I have 3 large groups here, then this approach is made impossible, right? And even if you were to rotate the bond, so the X is here, then this approach is impossible. So what we say is that in a case like this, a tertiary substrate, and a case where the alpha carbon is adjacent to a quaternary site, there is steric hindrance that prevents the reaction from occurring. And all steric means, steric refers to the size and spatial orientation of groups. So if groups are big and they're blocking the approach of my reagent, we say that they're offering what's called steric hindrance to the reaction. And we'll develop that concept in more detail when we look at SN2 reactions. But under normal circumstances, you can pick and choose which of the RXs you want to make into the nucleophile and which you want to leave as the electrophile. Because I must have a nucleophile attacking the electrophile. The only time it becomes an issue is when one of your RXs is at a tertiary or has the alpha carbon adjacent to a quaternary carbon, in which case you must make it into the nucleophile. So I'm going to just give another sort of illustration of this. If, let's say, I wanted to synthesize, this compound. Sure. Let's say I wanted to synthesize that compound. That looks weird. Let's say I wanted to synthesize this compound. And I say, I want you to design syntheses for that compound using the Corey-Posner-Whitehead-House approach. Well, the way I would interpret this is I'm going to look for what's called a disconnection. In other words, I know that fundamentally the Corey-Posner-Whitehead-House reaction makes a carbon-carbon bond. So I'm going to look, right? I'm going to look for the carbon-carbon bonds in the molecule, and I'm going to mentally disconnect along those bonds. So I'm going to illustrate. So I can consider this carbon-carbon bond. I'm going to call that one disconnection A. I'm going to call this one disconnection B. I'll call this one disconnection C. There's another carbon-carbon bond here. I'm going to call that disconnection D. Now there are carbon-carbon bonds within the ring. We never disconnect in the ring. We're going to treat the ring as a unit unto itself. We're going to treat the ring as if it's sacrosanct. Leave the ring alone. So what I'm going to try to do then is show how we can do this reaction for each disconnection. So I'll say disconnection and we're going to say what my Rx is, what my R prime X is, and who is my R2CuLi. And then I might give examples of the reactions. So let's call these disconnections A, B, C, and D. So I'll do the first one. I guess I'll do them all. So for disconnection A, what are my pieces? And as it's written here, I'll let the Rx be the one on the left, and the R prime X be the one on the right. So if I do this disconnection, what do I have on the left? Well, it'll be the cyclopentyl ring with the methyl. I've got a methylene, and then I've got this methylene. And attached to that is going to be some halogen. Let's pick chlorine. So just make sure we're following. So here is this carbon. It's got the methyl, right? It's got the methylene and the methylene. This is the bond that I'm disconnecting. So I know that the substrates for the Corey-Poisson-Whitehouse reaction are haloalkanes. So I'm going to have this carbon attached to a haloalkane, which means this carbon, which is methyl, right? That's going to be my other Rx. And it doesn't matter, I can make this the bromine. So these two halogens don't have to be the same. And my X could either be chlorine, bromine, or iodine. Again, we leave fluorine out. Okay. Does it matter which one of these is the cuprate? Well, how do I answer that? I'm looking to see if either one of these has a tertiary chlorhalide or a halide adjacent to a quaternary site. So that's methyl, that's okay. This is primary, and the primary is not adjacent to a quaternary site. So in this case, either one of them can be made into cuprate. So I'm going to say either, and my pathways could either be take the cyclic species, and I'm going to treat it first with lithium in dry ether, secondly with cuprous iodide, and then thirdly with methyl bromide. And that's going to make my product. Or, not or, but and, I could have done it the other way. I could have taken the methyl bromide, treated it first with lithium in dry ether, followed by cuprous iodide, followed by my cyclic species. Now, I should mention, there are lots of ways in which we can indicate the course of a reaction. I can write it out step by step by step, as we did in the very first case, or I can just summarize and say, here's my substrate. First, I treat it with lithium and dry ether. The assumption is I'm going to isolate my product from that reaction, make sure it's clean, then I treat it with cuprous iodide. I'm going to isolate the desired product from that reaction, right? Collect it, make sure it's clean and pure, run my spectroscopy and so on to do impurity. Then I treat it with my other reagent. So that's what this means. First step, include the cleanup and the purification and the confirmation. Second step, cleanup, purification, confirmation. Third, cleanup, purification, confirmation. And that's going to give you your product. So that's disconnection A. So I could do disconnection B. If I do disconnection B, so I'm doing here, who are my pieces? Well, the piece on the left is going to have the cyclopentyl ring again. Here is this carbon. But now I'm disconnecting here. So this carbon is going to be bound to a halogen. I don't really care which halogen it is. Let's be able to use iodine, let's use iodine. So what's my piece on the right? Well, it's got methyl and a methylene. So it's an ethyl group. So I'll have CH3, CH2, and it doesn't matter what this is, let's use another I. Okay, those are my pieces. Does it matter which one of them gets converted into cuprate? Well, let's see. Is either a tertiary halide or has the halogen on a carbon adjacent to a quaternary site? Well, this is the primary halide. This has no such issues. This one is also primary, but it has a carbon adjacent to a quaternary site. Therefore, I have no choice but to make this one the cuprate. So the cuprate has to be this compound. And again, I'm very deliberate in showing to which carbon the copper is bound. I'm showing where the nucleophilic site in the molecule is. It has to be here. So the only way this reaction could go, if I chose this connection B, and I don't have to, I could have done this connection A, it depends on what I have on my shelf in the lab, or which one of these things is cheaper when I order it from the company. Okay? So when I do this connection B, the way that's going to work is I'm going to take my iodide, and I'm going to treat it first with lithium in dry ether, followed by cuprous iodide, followed by ethyl iodide. And that's going to give rise to my product. That's this connection B. And there's no other way to do this connection B because this substrate must be converted into the nucleophile. What about this connection C? Well, this connection C, the piece on the left, would be, here's my carbon skeleton. Here's the bond that we're breaking, so this carbon must be attached to the halogen. Let's go, you have to use a Br in this column, let's use a Br here. I can pick any one of them, any one of the halogens. The piece on the left is then CH3, CH2, CH2, that's a propyl. So this is going to be CH3, CH3, CH2, and I can pick, let's do a chlorine, I guess, doesn't really matter. Does it matter which of these is made into the cuprate? Well, let's see. Who must be made into the cuprate? Well, either if you are tertiary or you have the alpha carbon adjacent to a quaternary site. Well, that's tertiary, so we are locked in. So we must make the cuprate from that species. And the cuprate we're going to need will be this one. And again, we're very clear to indicate to which carbon of the nucleophile the copper is bound. The only path I can take in this is to have the substrate, and I'm going to treat it with lithium in dry ether, and I'm going to put F dot B dot cuprous iodide. F dot B dot means followed by. So I can either write this as 1, lithium in dry ether, 2, cuprous iodide. Or I can say 1, lithium in dry ether, followed by cuprous iodide. That's the same as saying step 1 is lithium in dry ether, step 2 is cuprous iodide. And then I can say followed by, so if I want to do that, I'm just going to take out the 1. Followed by, this is N-propyl chloride. Right? And that's going to give rise to my product. And then as you might expect, in D, this connection D, my pieces would be, I could have